chapter 11. We'll talk about relays. We already talked about relays, but the book takes it a little bit 2 notches up. But we'll repeat the same stuff that we need to know all the time. We have 3 types of relays. So we're going to repeat these things over and over again. They're all the same. They have the same components, they just have different applications. So relay is below 20 amps, more 20 amps, more than 20 amps, plus what overload protection. If an equipment is drawing above 20 amps and there is malfunction in the equipment, the draw is going to be really high. So the error is going to be really high, so that's why we need to have magnetic protection. Parts and operation of contacts in the relay. We'll talk about the application of contactors, where do we use them and why. Correctly install a contactor or a relay in a control system. And I did say before that mainframe computers used to use small relays to open and close the circuits on and off and do a binary system. All the thinking module of traffic light used to be made out of completely just relays and timers. And I used to have an old controller here that's completely mechanical based on relays and mechanical timers. This is the past from the 70s. Probably you will not see this again. Sure. So if we look at it here, this is timer, mechanical timer, just like a cam, and it provides the sequence of operation. We have 2 mechanical relays here and a transformer. This chip here can be changed to give you this is for the flame detection system. We'll talk about these repeatedly and a lot next semester. But if you look at the mechanism, it's very interesting. And if you notice that they cover the entire board, so you don't even touch them, and nothing will do. So I highly doubt you'll see these in the field, but you might come across one of those
So
if you walk the road.
that's a contactor, you said?
The whole thing is a control.
Oh,
It's like a primary control, but for commercial, and it has a sequence of operation. It will turn off things on and off, but it's mainly mechanical. We'll talk about troubleshooting. Right off the bat, how would you troubleshoot a contactor or relay? What other things you want to look at? Coil, contacts, and mechanical linkage. So it's not that much. Yeah.
Those are the forms of all 3?
Yeah. They get to have different shapes, different mechanism, but those are the 3 main components. We'll talk about most overloads that we have in the field. Can you tell me what would you use to protect your circuit? What? Fuses? These are all like overload protections. So mainly either a circuit breaker or a fuse. And we'll talk about how they work. This type and why, and we'll talk about two concepts. Okay, what's an inductive load? What is induction? What is induction? Using magnetic wave to induce current into another component. So the motor works with induction, right? You have one current going opposite of the other. So that's induction. Your transformer is doing some kind of induction. There's a coil, a core. The core is magnetized. The magnet goes into the wires, and the wire gets current. So induction is when you don't see things, they're not touchy, but they're inducing magnetic field for power into the other. So can you give me an example of an inductive load? What's a load first?
Fan.
Exactly. So a load is anything that consumes power. So what's an inductive load? We say motor. What else? Fan has a motor.
TV.
TV is not inductive. There's no induction in the TV. Maybe there is, but not. How about coil? Transformer. What is a conductive load? Something that does not have to do with the magnetic field or inducing a field into other component. TV. I'm gonna say TV, but TV has a lot of components. I'll put it for you. What else? Non-inductive load, conductive load.
LED lights.
Huh?
LED.
Yes, lights.
Heating element.
Heating element. Capacitor. So let me solidify this information. Inductive load uses magnetism to either induce a magnet into the other component or to make current. So if we're using magnetism, that's inductive. This is the whole idea of induction. You have induction mode. Non-inductive or conductive load basically use resistance, heating light, capacitor, heating element. So write this down. It's going to be in the quizzes on Friday. Give an example of inductive. What is inductive? What is non-inductive? If there's anything to do with magnetism, it's inductive.
So it uses heat to transfer electricity?
Yeah. No.
Heat?
It makes heat. Yeah, it uses electricity to make something that has nothing to do with magnetism. Schematics will do that. We'll talk about magnetic starter, how to wire it, overload. So for control, it's going to be a good segue for control. If you look at this control system with you here in your hand, that is what we're going to study for the whole semester and the spring. What are the components? How do we make control? It's called combustion control. How do we make control? How to make things work by itself using electronic components? Otherwise, you're going to have somebody there at the switchboard turning things on and off. And it did happen at some point. Somebody had to be at the boiler room all the time, turning things on and off, and waiting and eyeballing things. Now everything has been done automatically. How do we control temperature? A lot of relays, and hopefully at some point, if you take a course with Bell for building management, you'll see how you control things remotely. Now we have the ability to let the boiler run by itself. We just do only one thing, which is what? Putting a temperature, and everything runs by itself. And that's thankfully that because we have some kind of control components, and we have timers. Functions, and again, sometimes the system failed. So if the system failed, we don't have somebody physically there to watch all the input, so we need to have overload protection. We also have low water cutoff, high water cutoff. So for the concept of control, you always have to have input and output and limits. And if you think about it, it's not that difficult, but how do we get this to go into action? And again, always think about your car. How did the car evolve? In the beginning, somebody had to go and crank up the car, and you had to control the clutch and the stick shift, and you have to listen too much, and you have to go do a lot of inspection in your car. Nowadays, cars do not need the inspection, you just turn and go. You don't even have to warm up your car, it takes care of itself. So that's why, because we have more and more control and more circuitry that will make the car perform even better. We'll talk about that again in a lot of details. Overload purposes. Contactors. So these are the contact and the contactors. For the contact, they are used for, it's a relay that will turn on low voltage control into high voltage load connection. So for the AC, you turn on the compressor, using the thermostat as the low voltage circuit, 24 volts. It will close a contact, and the contact will make a circuit that is 220. So imagine what would it be if you have the thermostat operating at 220. That's going to be a huge switch with a lot of wires. Meanwhile, the thermostat wire is gauge 18. It's very small. You don't want a lot of high voltage wiring into your house and into your controls. So it's better to have it this way. I remember in the past we used to have 220 ACs, window ACs. I used to dread turning it on. It would have this big switch and it's very heavy. I don't know if you still see it, but it's still there. It's very heavy to press. When you turn on, you see a spark inside. So you don't want that inside your house anymore. And that's why you have small, low voltage control inside your house. And you have the spark and the clicking and thing outside. It's safer. They don't have those anymore. Probably if you go into your laundry room, where you have your washer and dryer, and you can see this big switch over the dryer, over the water heater. This is a contactor with a swinging armature. So again, if we were to identify the components, this is my coil. It's wrapped up here to protect it. This is my mechanical contact, and you see this thing will be swinging back and forth. So it's going to be my mechanical linkage, armature, and these are the contacts here. And this spring will just give it some power, so it will be moving freely, because the contactor here will work only in one direction. So again, what would you expect to be the problem here? Either the spring will be broken, the contact here will be dirty, or something stuck in it, usually insects or moth. They get stuck in the middle, or ants, or whatever, or a leaf, or they just rusted. Or the coil is bad. The coil testing is very easy. You'll go with your ohmmeter and test the resistance of this coil. That's a different solenoid coil of contactor. This is the coil, and this is where the core that produces magnetic field. And the magnetic field is calculated in a way that will be enough to pull in armature or pull it out. Coils. So we spent an hour watching that video, that really cartoonish weird video, to talk about magnetism. We learned about the coil, how every wire has a small, invisible magnet around it. And if we have a coil, we are intensifying that magnet. That'll be strong enough to pull in armature and move components. So it has to do with the type of wire and the amount it's moving. Do you agree? How does it get intertwined, and how does it coil affect the power of the magnet? You can find 24 volts contacts or coils, which will have the small components for relays. I can go up to 480. You can have a coil that operates at 480, and that will produce a very, very strong magnet. Probably you'll see that if you go to industrial application. What about the ones that have in the junkyard to pull in cars? That probably is a 480 coil, and it's probably wounded different ways, back and forth, many times. It has enough power to pull in a whole vehicle. So look at the voltage of any contactor relay or plus use so you can look at them. Show them here. Contacts, they are the parts that are connecting the circuit together. So you can understand how it should be like very solid contact. If it's touching part way, it's not going to give you good contact. So you want something to snap in and stay. And that's why a lot of thermostat with the spiral, they have a magnet, just to a permanent magnet, just to make this the sticking snap action very strong. Not these ones, the old ones with the spring. So you want solid contact, you don't want it to be halfway. What happens if you have halfway contact? It will buzz, it will not give you good connection, and can overheat and cause spark or fire. Type of contact control loads, inductive and resistive. Yeah. I will show you the contacts. So this here are my contacts, and if you look closely, you can see how it's a flat surface, and you want it to be tight. You don't want it to be halfway. So you want, and you don't want to come slowly. You want it to come really fast. So it's snap action. You want the magnet inside here. This is the coil, and this is my solenoid. You want to pull right away and make the proper contact. And the springs are to give it some kind of push and pressure. And these are the terminals that will be connected. So this is going to go to the AC, and this is 220 volts, and this will be 24 volts here, and we'll just connect them together. This is another small relay, and this is 24 volts. Actually, hold on. The coil here is, come on, tell me. It's 120 volt coil. Another type of contactor. Did you guys do the board with Bill?
No.
For AC?
The boards?
Yeah.
Yeah, couple.
Yeah. So some of those boards, they have contactors, right? And they have low voltage and high voltage. So you get the concept of what are we doing. Again, the coil, you always have to make sure that the coil connects to the right voltage, otherwise it will burn. A lot of time people connect the coil when it's 24 to 120, and this is how you burn the board. The coil. The coil must be in good condition. Hardly ever becomes weak. Why would it become weak? The insulation in the wires get worn out, and two wires become one wire, and that will change the magnetic field around it. Contact must be in good condition, visually inspected. There is a contact cleaner specifically for contacts that will, over the time, there's a rust, there's a amount of rust that will form in the contacts, and they make a film that prevent the current to flow. So sometimes you can use a specific cleaning paper or a contact spray. Do not randomly just use any kind of sandpaper, because that will change the surface area. Mechanical linkage is visual inspection, and if you shake it and there's something rolling inside, you know the mechanical linkage is broken. With contacts, we do not repair anymore, and if it is repairable, you can call the manufacturer, but you change the entire thing. Just make sure you have the right model, and also make sure of the pins. What pin go where. So again, relays, open and close the circuit based on the input. They are used from fan motors, condenser fans, damper motors, whatever you want. And again, some boards have a set of contactors and some kind of logic control behind it, and sometimes some timers. The primary control has inputs and outputs, and also they can run the voltage through some timer. You can open some two contacts, but it will go through a timer. Timers are very easy. It's just a small integrated circuit component. You can buy from Radio Shack. Do you still have Radio Shack?
Maybe a couple places.
Yeah?
There's at least one Blockbuster one somewhere.
So you can buy a small chip that's just a timer, and you can connect it to the component. These are the contact relay. We've seen it here. And these areas you want to be very clean and producing good contact. How do you test that the contacts are actually connected? Oh, go ahead. How? You can measure it, right? What else? You can also just measure the connectivity. There's two ways. First, you can do continuity between this part and this part, but you don't know how much goes through it. So measuring voltage is really good. Like measure the voltage before and the voltage after. Are you getting the same thing or not? Overloads. So for all our contacts, for all our components, we always need an overload. There are a lot of different kind of overloads. And nowadays we use more overload protection because everything is completely automated. If you notice your car has a lot of lights in the board, those for like alarms or something is went wrong. And mostly a lot of them are just activated by overload or sometimes underload. In control, we'll talk about that in more details. But what can we control? We have three things, right, in a circuit. What are the three components of a circuit? Voltage, amperage, and resistance. So we're gonna play around these things to measure and to know how the circuit is doing. We're either gonna measure the resistance, or measure voltage, or amperage. And based on these, and also heat. But again, we transfer heat into, there's a relationship between heat and amperage, and there's a relationship between magnetism and electricity. So whatever tools we have, we use to make the best control possible. So fuse is the simplest way. It's usually for wired and non-inductive loads. Why? Can somebody tell me why we do not use fuse with a motor or an inductive load?
Draws a lot right off the
No, they have high voltage fuse.
It'll draw a lot right off the start up and the run
Yeah,
are different.
inductive load have a fluctuating usage or amperage draw. So if the motor gets stuck a little bit, just a spike, and it's going to blow the fuse. So you don't want something that will blow the fuse up. I remember again from the all the ACs, you turn the AC with that big switch, and they tell you to wait 5 minutes before you turn it again on. And if you don't, you blow a fuse. And they have two 20 amps fuse you put in the switch, which is very painful. So that was before having circuit breakers with protection. And also they changed the whole kind of compressors. They don't require as much voltage, and the whole idea became more for safety, so we do not have to do that anymore. So just to repeat, fuse are not used with inductive loads because they cannot handle the spikes that inductive loads do. It's not adequate. We can still have a fuse, but that should account for the spike. So we have a locked amperage and we account for that. So it's going to be the last measure. We're going to have inductive load and we also can have fuse. If you look at some circuit breakers, they have a circuit breaker and also have a fuse. The fuse is going to be oversized. It's for extreme cases. Resistive or non-inductive loads that are purely resistive in nature with no coil to cause induction. No coil, no magnetism. Example, heater, infrared lamps, timers, they're non-inductive. Fuses, any questions about inductive, non-inductive? Think you got it? So what about solenoid valve, inductive or non-inductive? Inductive. What about fridge door magnetic seal? Inductive. Magnets, coils, that's inductive. LED, non-inductive. Fuses, they consist of two ends or conductors with a piece of wire. That wire is specifically calibrated to melt at certain temperature. And we said as we increase the amperage, the temperature will increase. And if you look at it, they're sometimes made of mixture of nickel and lead. Lead is has very low melting temperature, so it just melts to protect your circuit. There's different wires. If the wire is rated at 15 amps, you put a 15 amps fuse on it, so it will melt before the wire melt. Circuit components and non-inductive loads. You'll see fuses a lot in circuits and in control circuits. So this is a fuse here. Show the fuse. This is the fuse. And this fuse is protecting the entire electronic component. It is not connected to the inductive load over here. So this is just to connect to protect the circuit inside the board. So most boards of this type, they have a small fuse, and the purpose is that the fuse will take the hit before the board burns. Do not, under any circumstances, bypass the fuse by putting a wire. A lot of people do that, and it's really not a good idea to do that. Line break or power duty overloads. Don't worry about those. Magnetic starters. They have 4 sets of contacts, open and closed depending on the coil action. This is contactors, and there's 4 sets of contacts. Magnetic coil. I don't know if I have an overload protection here. Here you go. That's a magnetic starter. And it has a reset button in it for the safety. Magnetic coil, close the contact. It has a lot of power that it will stay magnetized the whole time the equipment is on. And we have a set of overloads that will click out if the circuit takes more energy. Magnetic starter has to be NEC rated. You should not skimp on those. And if anything goes wrong, you do not open it. It's completely sealed. And again, the magnet has to be strong enough and consistent that the entire time it should be pulling in while the contacts, while the system is energized. So class of overloads and magnetic starters, some of them have bimetal relay, welded metals wrapped around the break to break the circuit. What are those? So we have 2 types of thermal protection in that magnetic starter. Either we have a bimetal relay, which are 2 metals. Once they heat it, they bulge and they cut off the circuit. For example, this one is hot. This is when it's not hot. So this is the bimetal. When it actually So when it's cold, It's shrunk and it does connect the two pins. When it's hot, it bulges and snaps out, and that's a bimetal relay. Thermal relay operates with heat, and when it gets hot, it snaps out, but it has nothing to do with bimetal. It just probably resistive, has some resistance in it, and it pops up. Molten alloy relay, it's a link of material that will melt, and you have to replace it. I'll show you a picture of that in this slide. Yeah.
So, magnetic starters, so like, let's say like, if something's wrong, does it just turn off the whole circuit?
Yeah. This is a molten protection. This piece here is to connect the circuit, and if it gets too hot, it will melt, snap out, and you can replace this piece. So this is
Talking cool, right?
molten alloy. It's refused. This alloy here has a pin that's put against gravity. It's filled with lead to connect the two terminals. When it's hot, this will melt, and the pin will drop, and the connection will, the circuit will be open. So that's another example. These are easy to inspect. You can visually see that the piece is molten, and you can see the pin has dropped, or you can see the equipment being charred a little bit. Ohmmeter, connect the two terminals, zero continuity, no connection, or look for molten parts. Usually it's you see it burn, and sometimes you can smell it smoking. Magnetic starter. Contacts, you can same issues all the time. Three things that we always go for. Contacts, solenoid coil, look for the overload in the magnetic starter, that's the thing in the bottom, and look for the mechanical link. Make sure all the links are not rattling and moving in the right direction. Must be treated as a unit. What does that mean?
One
Huh?
piece fails, the whole thing's failed.
Exactly. Did you guys pay attention to that? If one piece fails of the magnetic starter, you change the whole thing. We do not repair it. Push buttons stations. Push buttons are relays that you push, and you probably activated the magnet. Once it gets de-energized, it will snap back. So when you go to the elevator, all these are relays. There's a set of relay. If you look at the board behind the door, there is a bunch of relays, and you keep pushing them, you activate it. Once you reach the right floor, there's a coinciding magnet that will deactivate the relay. So these either you push them, they connect, or they don't. This is a snap action here. So once you activate it once, you hit it once, it goes back, you activate the coil. The coil will stay activated until it gets deactivated again. Don't get too much into this circuitry, but the idea, you know, if you push it, you activate the small magnet, and it will not be deactivated until something else pushes it the other way, which is usually another relay. So think of the elevator, push the relay gets stuck until the relay needs to match in the same floor, it will not get deactivated. Usually they put it actually in the top, the sensor will be in the top, and by the time it slows down, the elevator is in the right place. That's how the best way I can describe it. So what do you remember about relay? Three types: relay, regular relay, less than 20 amps; contactor, more than 20 amps; magnetic starter, more than 20 amps and overload protection; coil, contacts, mechanical linkage. What else? Inductive and non-inductive load. Can you remember these things? Okay. Don't remember these two. Again, as I already said, if the contactor failed, the system failed, because it has the power for the entire system. Coil, depending on the wire and the way it's wound. Contactors are rated by amperage. Remember this. Contactors are made out of silver and cadmium. The tips of the contactor here, the connection tips, are made out of silver and cadmium. Why?
Cheap?
No, silver is not cheap.
It's not cheap?
It's conductive and does not oxidize. And the oxidation on the silver, even if it does tarnish, it's still connected. With copper, if it oxidizes, the green stuff, it's not very conductive. That's why we use silver and cadmium. With conductivity, some contacts are made out of gold. Some parts in your computer CPU are made out of gold because of the best conductivity and less oxidation. This is the diagnosis. The simplest way to protect the fuse, a circuit is a fuse. Simplest and cheapest. We talked about conductive and conductive load.
So like in an elevator, it doesn't work. The whole machine.
It's not going to move. Yeah, but it's it used to be mostly mechanical relays, set of relays like these ones. Everywhere you hit it, energize. There's another sensor in the floor that will connect to it and de-energize it. It's very, very interesting mechanism. Okay. This is the last slide I have. Please remember it. Where is it? Come on, come back. Write this down. It's gonna be in the quiz inside. What is this? Yeah, it's single pole, single throw, double pole, single throw, single pole, double throw, which is different. Double pole, double throw. I'm gonna ask you to sketch those in the quiz Friday. So Friday, we have a quiz, and we'll start by the game that we didn't finish, the trivia game. So make sure you remember your team. And
You remember the points?
huh?
The points?
Yeah, I recorded them. All right. And extra credit project is due Monday. The paper for the other class. For here, we'll do on Monday. I will do a quiz extra credit if you guys need it or want it. What is it based on? The last 6 quizzes. Good. All right. We're all set.